Are we alone in the universe? This is the enigma that has stirred and puzzled the minds of thinkers, scientists, and dreamers alike for centuries. It's a question that straddles the line between philosophy and science, speculation and fact. And within this tangled web of thought, two intriguing theories stand out. First, we have the Drake equation. It's not so much a hard and fast formula as it is an intellectual tool, a way to stir conversation and provoke thought. It multiplies together a string of probabilities to give us a rough estimate of the number of civilizations in our galaxy that we might come into contact with. Then there's the Fermi Paradox, named after physicist Enrico Fermi. It's the seeming contradiction between high estimates of the probability of extraterrestrial life and the lack of evidence or contact with such civilizations. While these theories offer interesting perspectives, the search for extraterrestrial life begins with the search for exoplanets. Scene script. Exoplanets, or extrasolar planets, are celestial bodies orbiting stars outside of our solar system. These fascinating objects are formed much in the same way as the planets in our own solar system. They emerge from a disk of dust and gas surrounding a young star. Over time, these particles stick together, growing larger and larger until they form a full-fledged planet. But the type of planet that forms can vary greatly. Some exoplanets are terrestrial, much like Earth, Mars, and Venus. These planets have solid rocky surfaces and are often closer to their parent star. Then there are gas giants, similar to Jupiter and Saturn. These planets are primarily composed of hydrogen and helium, and they often have numerous moons and rings. Lastly, we have ice giants akin to Uranus and Neptune. These planets have a rocky core surrounded by a mantle of water, ammonia, and methane ices, with an atmosphere composed largely of hydrogen and helium. But where these planets reside in their solar system is perhaps the most intriguing facet of their existence. There is a region around each star known as the habitable zone, or the Goldilocks zone. This is the area where conditions are just right, not too hot, not too cold, for liquid water to exist on the surface of a planet. And as we know, where there's water, there could potentially be life. However, not every planet in the Goldilocks zone is necessarily hospitable. The planet's atmosphere, magnetic field, and geological activity all play a role in its potential habitability. But the fact that these zones exist and that we've discovered planets within them is a tantalizing hint that we might not be alone in the universe. The discovery of these distant planets is no easy feat, but every exoplanet we find brings us one step closer to answering the age-old question, are we alone in the cosmos? Or is there somewhere out there a planet much like our own, teeming with life? Only time and the continued exploration of these incredible exoplanets will tell. The vastness of space makes finding exoplanets akin to spotting a firefly against a spotlight hundreds of miles away. It's a daunting task indeed. But thanks to the prodigious advancements in technology, we have developed methods to detect these elusive celestial bodies. Primarily, there are two methods to detect exoplanets: transit photometry and radial velocity. Let's delve a bit deeper into these techniques. Transit photometry is a bit like watching a tiny eclipse. When an exoplanet passes in front of its host star, it causes a small decrease in the star's apparent brightness. By monitoring these slight dimming events, which typically last a few hours and cause the star to dim by about 1% or less, astronomers can determine the planet's size and its distance from the star. The smaller the planet, the lesser the dimming, and the farther the planet from the star, the less frequently the dimming events occur. On the other hand, the radial velocity method exploits the gravitational tug-of-war between the star and its planet. As the planet orbits the star, it causes the star to wobble slightly. This wobble creates a shift in the star's spectral lines that astronomers can detect as a Doppler shift. By monitoring these shifts, astronomers can infer the presence of the planet, its mass, and its distance from the star. Now let's talk about the Kepler Space Telescope, a veritable planet hunting machine. Launched in 2009, Kepler's mission was to survey a portion of our region of the Milky Way to discover Earth-sized exoplanets in or near habitable zones and determine how many of the billions of stars in our galaxy have such planets. And indeed, it has been a resounding success, contributing to the discovery of a significant number of exoplanets. These methods have led to the discovery of thousands of exoplanets, with more being discovered every day. The hunt for these distant worlds is far from over, and who knows what exciting discoveries await us in the depths of the cosmos. Despite the challenges, the field of exoplanet research is thriving. We stand at the precipice of a new era of discovery, with recent advancements propelling us further into the cosmic frontier. Let's take a moment to appreciate some of these significant milestones. Firstly, let's talk about Proxima Centauri b, an exoplanet that orbits the star closest to our Sun. Discovered in 2016, it's a rocky planet just a little larger than Earth and resides in the habitable zone of its star. This means it could potentially hold liquid water on its surface, a crucial ingredient for life as we know it. The discovery of Proxima Centauri b has sparked immense interest and has become a significant focus in our search for extraterrestrial life. Moving on, let's discuss an instrumental tool in our cosmic exploration, the James Webb Space Telescope. Launched recently, this revolutionary telescope is set to supersede the Hubble Space Telescope in terms of capabilities. With its advanced infrared capabilities, it will peer through cosmic dust to observe the formation of stars, galaxies, and yes, exoplanets in unprecedented detail. It's a true testament to human ingenuity and our relentless pursuit of knowledge. Now let's shift our focus to the role of artificial intelligence and machine learning in exoplanet research. With the vast amount of data generated from telescopes, it's become increasingly challenging to analyze it manually. Enter AI and machine learning. These technologies are being used to sift through the data, identify patterns, and detect potential exoplanets with impressive accuracy. They're becoming indispensable tools in our quest to understand the cosmos. As technology advances, so too does our understanding of these distant worlds. Each discovery brings us a step closer to answering the age-old question: are we alone in the universe? The current state of exoplanet research is indeed promising, and we're excited to see what the future holds. The search for exoplanets is not just about finding new worlds, but about seeking answers to our most profound questions. The future of this fascinating field is bright, brimming with promise and potential. Advanced missions and technologies are on the horizon, each with the potential to revolutionize our understanding of the universe. Consider the Transiting Exoplanet Survey Satellite, or TESS. This mission, led by NASA, is designed to survey the brightest stars near the Earth for transiting exoplanets over a 2-year period. TESS is expected to catalog more than 20,000 transiting exoplanets, including 1,000 or so that are approximately Earth-sized or super-Earth-sized. The data from TESS will provide us with precious clues about the compositions, atmospheres, and structures of these distant worlds. Then there's the Planetary Transits and Oscillations of Stars mission, or PLATO, led by the European Space Agency. Scheduled for launch in the late 2020s, PLATO is designed to search for Earth-like planets around Sun-like stars. It aims to measure the seismic activity of the stars to determine their masses, sizes, and ages, all crucial information for understanding the nature of exoplanets. But the real game changer in the future of exoplanet research might be the potential to find biosignatures or signs of life on these distant worlds. Biosignatures could be anything from certain gases in a planet's atmosphere to evidence of water or other key elements. Finding these signs would not only confirm the existence of life elsewhere in the universe, but also give us invaluable insights into how life can evolve and survive in different environments. The future of exoplanet research is a thrilling journey of discovery, one that promises to deepen our understanding of our place in the cosmos. As we continue to gaze into the stars, we inch closer to answering the question, are we alone?